Good evening, Blackpool. A pleasure to be with you again, this time virtually. I'm talking about warping, space and time. In other words, the science fact and a little bit of the science fiction behind black holes. So I'll be doing a very brief history, that means just 1 or 2 slides on the history, and then looking for most of this talk at the science facts. And at the end, I'll be delving into a little bit of the science fiction and where Hollywood usually gets things wrong. And then I will just have a very quick think about the future. So, the very brief history. Now, just to get the definition sorted so we're all on the same page. A black hole, strictly speaking, is not an object, it's a region of space from which nothing, not even light, can escape. And if you think about when the concept of a black hole originated, it's probably earlier than you think, unless you happen to be a historian and you know about these things. Because we tend to think about black holes as being sort of thought about in the middle of last century. But in fact, the idea goes back to 1783, when the Reverend John Mitchell came up with this statement, which I'll paraphrase. If you think of a star that's 500 times bigger than the sun, but the same density, then the mass will be such that all light emitted from such a body would be made to return toward it by its gravity. So even back then it was understood that if you have something massive enough, if you have enough mass in a certain volume, it might be that gravity is so powerful even light cannot escape. But in the 1800s, the idea of these so-called dark stars, that they were essentially forgotten for over a century, and the idea didn't come back again until the early 1900s, when Einstein came up with his general theory of relativity. I'm not going to go through all of this detail, but here are just some of the key players and dates if you wanted to go and find out a little more for yourself. But the bottom line is that Einstein in 1915 came up with the general theory of relativity, which talked about the nature of how mass changes space. And various people picked up on his equations and started applying them, especially to what happens if we have a lot of matter in a small volume. So Schwarzschild basically calculated what happens when you have a very compact star. And it was found that very odd things happen when you take a certain mass and compress it to a certain size. You get this odd situation where the escape velocity, which we'll come to shortly, can exceed the speed of light, and also it appears that time stands still. Hence the comment in the bottom right there, if time actually stops when you reach this particular size of a mass being compressed into a small volume, you can think of these stars as dark stars if light doesn't escape, but you can also think of them as frozen stars, frozen in the sense that time is frozen at this so-called Schwarzschild radius, which is the point at which really strange things start to happen when you compress a very large mass. So, in order to get some understanding of what black holes are all about, I think of this in terms of 4 pieces of the puzzle which we need to think about. And those 4 concepts that we need to deal with are, firstly, the idea of escape velocity, so we can understand what we mean by a black hole, meaning escape velocity reaches the speed of light. So that's the first concept we've got to deal with. We need to think a little bit about general relativity, but you'll be glad to know we're not going to go through the maths of general relativity. We'll have a think about stars and galaxies and how black holes are formed. And we'll think about how we detect the existence of black holes. If we can't see them from light escaping from inside the black hole, how can we detect these gravitational objects? Now, in principle, we need to have a think about each of these 4 pieces of the puzzle. We don't have to do them in any particular order, but I'm going to cover them in the order I've just described them. And to try and allow you to follow what I'm saying, I've color-coded each of them. And as we go through each of the sections, the particular little graphic there of the 4 pieces of the puzzle, I'm going to put those in the top left-hand corner to make it a little bit easier, hopefully, to follow which section are we dealing with. And if you want to look at the handout of the slides, which I'll make available to you afterwards, I'll send you the link. then the handout of the slides again has the same color coding to make it a little easier to follow where are we up to. So the top left-hand piece of the puzzle is escape velocity. Well, the escape velocity, how fast do you have to throw something from the surface? Let's just assume that we're talking about objects which are spherical, because that just makes life easier. If we're on the surface of the Earth or the surface of the Moon or surface in principle of a star, how fast do we have to throw an object in order for that object to coast to infinity and escape the gravity of the body? Well, it turns out, again, I'm not going to go through the maths, but it turns out if you want to calculate escape velocity, it only depends on that ratio, the mass of the object we're talking about and its radius. This is assuming that we're calculating the escape velocity at the surface of a body, in other words, at a particular radius. The escape velocity only depends on the ratio of the mass to the radius. We can actually calculate some values. For instance, if we say what is the velocity needed to escape from the surface of the Moon, turns out to be 2 kilometers per second, 5,000 miles an hour. If we compare that with the escape velocity of the Earth, we find that is 11 kilometers per second, or about 25,000 miles an hour. So that, roughly speaking, is the velocity that was needed to be gained by the Apollo astronauts in order to escape from the gravity of the Earth and basically coast on their way to the Moon. You can see that getting back was easier because it needed a much lower escape velocity to escape from the Moon and then return to the Earth. If we calculate the escape velocity of the Sun, being a very much larger mass, yes, it has a larger radius as well, but a much larger mass, turns out the escape velocity at the surface of the Sun is about 600 kilometers per second, or more than 1,000,000 miles an hour. And that sounds ridiculously fast, but remember that's only a tiny fraction of the speed of light. The escape velocity from the surface of the Sun is only some 0.2% of the speed of light. But if the escape velocity depends only on the mass divided by the radius, then we can do a little thought experiment and ask what happens if we take the Sun and compress it into a smaller volume. In other words, keeping the mass the same, what if we make the sphere of the Sun a smaller radius? If the escape velocity depends on m divided by r, and we keep m the same and make r smaller, then the escape velocity is going to go up. And we can plot that on a little graph showing what happens if we were to theoretically compress the Sun into smaller and smaller sizes. So the vertical scale of this graph is showing us escape velocity in kilometers per second, and the horizontal scale is showing the radius. Now the actual size and escape velocity of the Sun are shown by the yellow dot there, roughly 600 kilometers per second. If we were to take the mass of the Sun and squeeze it into a smaller volume, the escape velocity would be higher. A smaller size still, the escape velocity would be higher. Remember, we're just calculating an escape velocity by calculating m over r, mass divided by radius. And if we squeeze the Sun down until it's only the size of a small country, then the escape velocity would be higher still and would be some 30,000 kilometers per second. If we squeeze the Sun down until it's the size of a city, the escape velocity would be higher still. And finally, if we squeeze the Sun until its radius is about 3 kilometers, then we reach this point such that the escape velocity reaches the speed of light. And at that point, we will have made a black hole, because nothing can escape, because nothing can move faster than the speed of light. This particular point, this 3 kilometer point for the Sun, we talk about an event horizon, a sort of membrane, if you like, or a one-way surface, in the sense that things can fall in, but nothing can escape. That particular radius is called the Schwarzschild radius, after the work of Schwarzschild back in 1916. So the event horizon exists at what we call the Schwarzschild radius. 3 kilometers simply happens to be the value for our Sun. Our Sun has a particular mass, and that gives us a particular radius for the event horizon. If we were to take something else, for instance a smaller mass, we would end up with a smaller Schwarzschild radius or a smaller event horizon. If we start with a body, for instance, which is the mass of the Earth, then the radius of the Schwarzschild radius would be of order centimetres or so. If we were to start with a mass equal to the mass of the Moon, then the Schwarzschild radius would be barely the size of a grain of sand. And if we start with a mass, let's just say arbitrarily, let's take something with the mass of Mount Everest, the event horizon would only be about the size of an atom. All of these things we can calculate because, thanks to Einstein's general relativity, we can calculate how things behave when we take a certain mass and squeeze it into a certain volume. Now, we know of no way where we can actually do this. We do not have the technology that allows us to compress the Earth down to a few centimetres, or to compress Mount Everest down to the size of an atom. But just because we don't know how to do it doesn't mean it's impossible. Theoretically, if you could put that much mass in that much volume, you would generate a black hole. So that's escape velocity. Now let's think a little bit about what Einstein had to say back in 1915, the theory of general relativity. Now we're not going to talk about the maths, but what the hell, I'll show you one equation. This is deceptively simple because each of the elements here contains an awful lot of complexity. But what effectively that says is that on the left-hand side of this equation, that's telling you about the geometry of space. And the right-hand side of the equation is telling you about the mass and energy that exists in space. So you could, if you like, take all of the horrible mathematics of general relativity and reduce it to a much more prosaic description of what Einstein was trying to say. And that is, mass changes space. If you like, mass tells space how to curve. It warps or changes space, and as a result, space tells mass how to move. Now that doesn't encapsulate all of the elegant maths that Einstein put together, but it gives us an idea of what's going on. Mass and space are interrelated, and they are not independent. Mass affects space, and space affects mass. But what do we mean when we talk about warping space or perhaps curving space? Now, if we try and imagine what's going on, most people resort to a two-dimensional analogy and talk about a sheet of paper representing the universe, and then what happens if we flex or warp or curve that piece of paper. Because we can take a two-dimensional piece of paper and curve it into a third dimension. But how on earth do we warp three-dimensional space? Well, mathematically it's possible, but we find it essentially impossible to visualize that because we cannot visualize three dimensions curving into a fourth dimension. Humans simply are not built with that amount of imagination. So Einstein, with a little bit of help, managed to deal with the maths, and the maths doesn't care about the fact that humans can't visualize three dimensions curving into four dimensions. But effectively, we still end up resorting to a two-dimensional way of thinking and then saying that, well, actually the universe is three-dimensional, but this is the best picture we've got. Imagine a two-dimensional flat surface. If we were to place a large mass, such as a black hole or a very large mass object, regardless of whether it's a black hole or not, it will start to distort that two-dimensional curve, and ultimately a black hole will produce infinitely distorted or infinitely warped space. So all of the artist's impressions we ever see of a black hole always have this sort of idea of a two-dimensional analogy, of a sort of plug hole, if you like, where we can imagine matter falling into the plug hole and falling into the black hole. Why do we think that general relativity is right? In other words, it gives some rather odd results, but we think general relativity is right because it's made a few predictions which have been shown to be correct. For instance, the orbit of Mercury, although it looks like an ellipse, that ellipse is slowly rotating or precessing around the Sun. So strictly speaking, it's not an ellipse. It's something that's almost an ellipse, but it doesn't quite close on itself. and the distance of closest approach of Mercury to the Sun, the perihelion, slowly rotates around the Sun. Only very small amounts, it's measured in arc seconds rather than degrees, but Newton could calculate that but didn't quite get it right. Newton got more than 90% of the precession calculated but didn't quite get the right result. When Einstein's general relativity was applied to the precession of Mercury, it basically got the answer correct within the error of the observation itself. So there was observational evidence that Einstein's general relativity does, in some cases, a better job than Newton's description of gravity. The same was true of so-called gravitational lensing, the fact that when light passes an object, such as the surface of the Sun, it can bend, it can be distorted, as if the mass is behaving like a lens, so-called gravitational lensing. So if you have distant stars, which the light from which is passing close to the Sun, of course we can only see those distant stars during an eclipse. So in 1919, when an eclipse occurred, the measurement of the positions of these stars was noted to see whether or not they were out of position compared with the known positions of the stars, indicating that the light on passing the surface of the Sun was being deflected due to gravitational lensing. Again, Newton can calculate how much we would expect, but Newton doesn't give us quite the right answer, whereas general relativity does. So we have observational evidence that bolsters the idea that general relativity seems to be the correct description of how gravity behaves. But this idea that extreme mass, or a large mass in a small volume in particular, can distort space is one aspect of what general relativity had to say, but it also predicts that time is warped by the existence of strong gravitational fields, and close to a black hole, time will slow down. Now, that's a very difficult thing to get your head around, but again, there were very distinct predictions of general relativity, and this has been tested. Some years ago, they took some atomic clocks and they synchronized a whole load of clocks, some of which stayed on the ground and some of which were flown in a jet from east to west and from west to east at various heights. So because we know that the special theory of relativity says that time is affected by the speed at which something moves, that has to be taken into account. But by flying the aircraft in different directions, that can all be taken into account. And by flying at different heights, you're flying in different gravitational fields because you're at different distances from the centre of the Earth. And these flights of atomic clocks, when they were then checked when the plane returned to the airfield, it was shown that indeed time does slow down depending on the gravitational field in which your clock is sitting. This is actually quite important because if you're getting information, for instance, from GPS satellites, each of which have atomic clocks on board, not only do you have to take into account the speed at which the satellites are moving, you have to take into account the height of the orbit in which the satellites sit, because they will all be experiencing slightly different gravitational fields, and hence the atomic clocks will run at different speeds. And this has to be taken into account if you want to get the most accurate GPS fix that you can. So although some aspects of general relativity sound very obscure, there are some real-world applications for applying Einstein's special and general theories of relativity. One of the perhaps rather more bizarre predictions of general relativity is that it predicted that massive objects will emit gravitational waves. In other words, not so much a very large mass sitting on its own, but very large masses that are moving, especially relative to each other, such as two massive stars orbiting each other, or two neutron stars orbiting each other, or two black holes orbiting each other, will produce gravitational waves. Waves in space, strictly speaking, and time as well, but waves in space are the easier ones to visualize. If we imagine gravitational waves moving through a cylinder, such as a pen or a pencil, if it's moving along the length of the pen, then gravitational waves will distort not the length of the pen along the direction of motion of the gravitational waves, but perpendicular to the motion, it'll distort a circular cylinder such that it gets stretched in one dimension and squeezed in the other, and then a fraction of a second later, the opposite way round. So you can see that the cross-section that was originally circular is now stretched into an ellipse one way and then stretched into an ellipse the other way. And as the gravitational waves pass through the object, the distortions of space will produce the distortions of the object. This particular animation is enormously exaggerated because the animation would imply that we're stretching and squeezing an object by maybe 10% or something like that. But no, the prediction of even if you have black holes orbiting each other, then what are you likely to see here on Earth? Well, you're likely to see distortions that are no bigger than not 10%, but more like 1 part in 10 to the power 20. In other words, it was assumed, although this prediction was made 100 years ago, it was presumed that we would never be able to measure anything quite so small. But despite the fact that plenty of people assumed it would be impossible to measure tiny distances like that, attempts were made, and I'll come back to detecting gravitational waves in just a short while. So we've dealt with escape velocity and we've dealt with general relativity. Now let's have a quick think about stars and galaxies. Stars can form black holes, and galaxies appear to have black holes at their heart. So we believe, from our understanding of stellar evolution, which is the topic of a different talk, we believe that massive stars, when they come to the end of their lives, if they're massive enough, they can end their lives in a supernova, and that supernova can leave at its core either a neutron star or possibly, if the core is compressed enough, a black hole. So a neutron star would only be kilometres or so in size, and remember, for something like the mass of our Sun, once you're smaller than 3 kilometres, you've generated a black hole. So the precise mechanics of how supernovae work are still being researched, but it seems like we have a reasonable understanding of the death of massive stars producing black holes. This, of course, the image you're looking at is just an artist's impression, which is rather fanciful, showing a planet being destroyed by a star going supernova. If another star gets too close to a black hole, then the tidal forces on the star can disrupt the star and completely shred it. Notice there was a black hole lurking on the left-hand side, which we didn't see until a passing star got shredded and the material of that star started getting sucked into the black hole. We can see that not all the matter goes into the black hole immediately. Let's just run that animation one more time. Either dust or gas or the material from a star cannot go into the black hole all at once. Like water leaving a bathtub, it will tend to circulate before going into the black hole, and what's called an accretion disk will form of lots of matter, in a sense, waiting its turn to go into the black hole. All of this matter orbiting around the black hole gets very hot, and so the accretion disk around a black hole might be visible. It might be radiating visible light or infrared or radio waves or X-rays, depending on exactly how hot this material is getting. Also notice that in some cases we see these enigmatic jets that are formed coming out of the region of the black hole. Not from inside the black hole, but from the region immediately outside the black hole. Now, the mechanism by which these jets are formed, very highly energetic material, particles being emitted from the black hole, we don't fully understand the mechanism by which that occurs. It's related to the infalling matter, providing a great deal of energy, and it's related, we think, to the magnetic fields that exist in the region around the black hole. But the mechanics, the details are still missing. But we do know that anything getting too close to a black hole could be disrupted by the tidal effects, and if you believe the popular media, this is called spaghettification. Okay, I guess we can call it that if you like, otherwise known as the noodle effect. If you were getting too close to a small black hole, if you went in feet first, the gravity at your feet would be substantially stronger than the gravity at your head, and hence you would be stretched out and, no doubt, killed before you actually passed the event horizon. So accretion disks definitely form. Sometimes we see X-rays, sometimes we see jets. Details yet to be worked out. If we look at the centre of the Milky Way, we see what appears to be a black hole right at the centre. For years we've been watching a few stars very close to the centre of the Milky Way, and we appear to see that they are orbiting something. The circle here is something we cannot see. So we see lots of stars that are orbiting in elliptical orbits, and it's clear they are orbiting something. And from the size of these ellipses and the speed at which the stars go round these ellipses in only a few years, remember it takes hundreds of millions of years for the Sun to go round the Milky Way, but some of these stars are orbiting in only a few years. And they're orbiting something that's quite small, otherwise the stars would hit it if it was that large. Small, and yet we can't see it. So it appears to be something very massive, but very small, and we can't see it, so we deduce it's a black hole. How big is it? Well, we deduce from looking at those star orbits that whatever is holding those stars in place, it seems to have a mass of 4 million solar masses. So this symbol on the right here, capital M circle dot, is just a symbol meaning the mass of our Sun. There's nothing special about the mass of our Sun, it's just a convenient unit. It's a more convenient unit than using kilograms or tons. So 4 million times the mass of our Sun is an object sitting at the centre of our Milky Way. And I've got the solar system here, let's just dim it down a little bit. The size of this object, remember we can work it out by knowing for a given mass what the event horizon radius or the Schwarzschild radius would be. We calculate that it's going to be substantially larger than our Sun, but much smaller than the orbit of Mercury. That's by no means the biggest supermassive black hole that we know about. We call them supermassive simply because they are very much massive than much more massive than the sort of black holes we expect to get by the death of a massive star, which might only be a few times the mass of our Sun. When we look at other galaxies, we find even larger supermassive black holes. For instance, the one at the centre of the Andromeda galaxy is some 250 million solar masses. And on a scale of our solar system, that black hole would be about the size of the orbit of Jupiter, as indicated on the right there. If we look into the middle of the Sombrero galaxy, we deduce that there's a supermassive black hole of 1 billion solar masses. And that would be even larger still. That would be larger than the orbit of Uranus in our solar system. And one of the largest we've seen to date, I'm not sure it's still the record holder, but there are definitely some black holes out there that seem to have a mass of greater than 20 billion solar masses. So large that I can't really fit it on this diagram other than squeezing it into the bottom right-hand corner there. So you can see that some supermassive black holes are literally enormous. They are larger than our solar system, or at least very much larger than the orbit of Pluto. Still very small compared to the distance between stars, but very large on our local neighbourhood scale. Interestingly, fairly recently, the Hubble Space Telescope has detected, or at least inferred, the existence of a massive black hole at the centre not of other galaxies, but at the centre of a star cluster within our own galaxy. Not at the centre of the Milky Way, but in a star cluster somewhere else in the Milky Way. So if it's possible that a few star clusters of maybe thousands, maybe tens of thousands, maybe hundreds of thousands of stars, if they have black holes at their centre, is it possible that essentially all clusters do, but we just haven't noticed them yet? It's an interesting question. If all galaxies seem to have a supermassive black hole at the core, is it possible that smaller stellar structures like star clusters, open star clusters or globular star clusters? Is it possible that they have large black holes at the core as well? We haven't got enough data to show whether that's the case or not, but it's an intriguing possibility. So we've looked at escape velocity, we've looked at general relativity, we've thought about the existence of black holes and supermassive black holes from the death of stars or from the centres of galaxies. Now let's take the fourth piece of the jigsaw, which is how we detect the existence of large, very dense gravitating bodies, such as black holes. About 10 years ago, the LIGO observatories, the observatories shown here, these big L-shaped objects in Hanford and in Louisiana, you can see that they are 3,000 kilometers apart. These LIGO observatories, LIGO standing for Laser Interferometer Gravitational Wave Observatories, these were built more than 10 years ago, and they've been operational ever since, and they've been refined and upgraded to try and make them as sensitive as possible, with the intention of trying to measure these gravitational waves. Remember, if they do exist, we would expect them to be very, very, very small in terms of the effect they have on anything here on Earth. And these interferometers basically take a laser, split the laser, and send it shining down these two very long arms of the L. They bounce off lasers at the very end, bounce off mirrors at the very end, and the laser light comes back to this central building. Remember what we were saying about gravitational waves earlier? If they're passing through an object, it'll tend to make the object stretch in one direction and then in the other. So if gravitational waves pass through an object such as this observatory with two long arms, what you would expect is that one arm will stretch ever so slightly and the other one shorten ever so slightly, and then vice versa. So we'll get a shortening and lengthening of the two arms backwards and forwards and backwards and forwards. So what that means is if we send a laser down one arm and bounce it off a mirror and come back again, and do the same with the other laser beam, as the two arms get longer and shorter as the gravitational wave passes through, that means the length of time it takes the laser to go down the arm of the interferometer, bounce off the mirror and come back again, those two travel times will be slightly longer and slightly shorter. So there'll be an interference of the laser beams as they come back, because they won't arrive at the same time. If they originally arrived at the same time without a gravitational wave, one would be slightly ahead and one would be slightly behind those times because of the lengthening and the shortening of the two arms. The mirrors at the end of these arms are very large mirrors, held in a sort of a pendulum, if you like, because the last thing you want is your mirror vibrating. Remember, we're trying to see tiny, tiny changes in the distance. Although the arms are 4 kilometers long, that's not much when you're trying to measure differences of 1 part in 10 to the power 20. Remember, that's the sort of sensitivity we're looking for. So you don't want your mirror vibrating backwards and forwards, masking the effect of a gravitational wave passing through your observatory. After bouncing off these mirrors and going back to the central part of the L, it goes through, the two laser beams go through a very complicated interferometer to try and see tiny, tiny changes in the length of time it takes the light to go along one arm and back or along the second arm and back. Technologically, many people said that this would just be impossible. But amazingly enough, 10 or so years ago, they actually declared that they had found a signal. Back in February of 2016, it was announced that LIGO had detected gravitational waves. They deduced that what they were looking at was two black holes orbiting each other, merging together into one black hole, which then settled down. And the signals that they produced are shown by the red and the blue wiggles there. Now, I'm sure anybody looking at that would say they're just wiggles. Isn't that just noise? But if you look carefully, you'll realise that there are characteristics between the red and the blue that seem to reproduce. And that's the reason that they had two different LIGO observatories, one in Hanford in Washington State, the other in Livingston in Louisiana State, separated by 3,000 kilometers. At that sort of separation, you would not expect to see the same signal in both observatories unless you were measuring something cosmic. If somebody stamped their feet or banged a door or a train went by, you wouldn't expect to pick up the same signal at both observatories. And so the signal that they were seeing, notice the timescale here is only a fraction of a second or so. The signal they were seeing, the scale here is how much has the distance changed that they're measuring as multiplied by 10 to the power minus 21. So we're looking at sort of 1 part in 10 to the power 21. 1 part in, what is that? 1,000 million. And we're seeing essentially just noise to start with, but then a signal starts to show itself. Small amplitude and relatively long wavelength, and then it gets larger and larger and faster and faster and faster, and then disappears. And in the other observatory, what do we see? We see essentially noise. Then we start to see a signal which is relatively small amplitude and long wavelength, and then it grows and grows and grows and gets faster and faster and faster and then disappears. In other words, these two signals are basically the same shape. Yes, there's noise on top, but statistically speaking, it is extremely unlikely that by random chance you would get these two signals that effectively overlay each other and show the same variation from two observatories that are 3,000 kilometers apart. Although the wiggles might not look very spectacular, the theorists got hold of that and tried to work out how can we explain a gravitational wave signal that looks like this, changing amplitude, changing frequency, and then disappearing. And they deduced that they were looking at the merger of two black holes. From the actual shape of these wiggles, they deduced that what we were looking at was the merger of two black holes. One of them was 29 solar masses. The other was 36 solar masses, and they merged together to produce a final black hole with a mass of 62 solar masses. Now, those of you who are good at maths will know that 29 plus 36 does not equal 62. 3 solar masses appear to have gone missing after these 29 plus 36 solar masses merged together to give us a black hole of 62 solar masses. They deduce that 3 solar masses winked out of existence and were converted, E equals mc squared, into gravitational waves. Just remind ourselves how much energy that is. Our sun should live for about 10 billion years or so, and in the process it will convert less than 1% of its mass into energy. When it converts hydrogen into helium, only about 0.5% of the mass is actually converted into energy. And that 0.5% is converted into energy over a period of 10 billion years. But here, not 0.5% of a solar mass, but 3 entire solar masses have been converted into energy, remember the timescale, over a few tenths of a second. So the amount of energy pouring out of this event was absolutely huge. It's estimated that the amount of energy coming out of this black hole merger for this fraction of a second was probably larger than the amount of energy coming out of all of the stars in all of the galaxies in the entire observable universe. That one event was pouring out more energy for that fraction of a second than everything else in the observable universe put together. That is a phenomenal event. And it's because it was such a huge event that that was the first event that LIGO saw. It's now analysing data and seeing more and more mergers of black holes and indeed neutron stars as well. More interferometers are being built on the surface of the Earth, and there are now plans to build an interferometer out into space. On Earth, we're limited by how far we can send the lasers. Remember, the LIGO arms, a laser is sent backwards and forwards along arms that are 4 kilometers in length. But if you put lasers in space, you no longer have that limitation. You can bounce lasers between 3 satellites, and you can separate those satellites almost arbitrary distances. They've decided that the best way of doing it is to have the arms of this particular interferometer, 3 satellites with lasers bouncing back and forth between them. You can have these arms millions of kilometers in size. And so that's the plan, to put up satellites and bounce lasers back and produce interferometry on a much larger scale. With much larger arms, you will be able to see much larger black holes changing more slowly than the very rapid merger of black holes that was seen with the LIGO interferometer. So this is called ELISA, the Evolved Laser Interferometer Space Antenna. Now we know that LIGO is sensitive to gravitational waves such as neutron stars colliding or black holes colliding. That tends to happen over a fraction of a second, and that's what LIGO is sensitive to. But that doesn't happen too often. It's hoped that ELISA, working with much longer arms of its interferometer, will be sensitive to events not happening on a fraction of a second, but over seconds, minutes, hours. And hopefully it'll be sensitive to changes undergone by supermassive black holes rather than individual stellar mass black holes. It's also been hypothesized that if we do build ELISA, which hopefully will be built within the next decade or so, then it might be possible to see gravitational waves from the biggest event of the universe has known, the Big Bang. Surely the creation of the universe must have produced a disturbance which has sent gravitational waves throughout the universe. So maybe they can be detected if we put these gravitational interferometers into space. In terms of actually identifying or seeing black holes, remember we can't see any of the energy coming out from inside the event horizon, but we can in principle see what's going on just outside the event horizon. And for that reason, a number of different radio telescopes were put together collectively to all look at a specific object, and the output of these various radio telescopes was then combined. Each of them was recorded, and then the recordings were put together, and then an image generated from each of these signals produced by these radio telescopes. Because they were spread over the entire Earth, in effect, they make a large radio telescope whose size is about the size of the Earth. And therefore, you have a chance of getting the sort of resolution that you would need. One dish would not be large enough, but a dish the size of the Earth would have the resolution to be able to see what's going on close to the supermassive black hole at the centre of our galaxy. But also it was decided to look at another object, M87. The galaxy M87 is 1,000 times further away than the centre of our galaxy, but its supermassive black hole at its core is perhaps 1,000 times more massive. And it's then been predicted that the accretion disk might be the same sort of size on the sky as the Milky Way's own supermassive black hole. So this is the image they produced. Clearly it doesn't show a huge amount of detail because the resolution of the telescope, even taking into account that it's the size of the Earth, because of the huge distance to M87, the resolution only shows us a few blobs, but it definitely shows us something that looks vaguely like a donut, which we interpret to be the accretion disk forming around this black hole. No light is coming from this central region because the gravity is so strong in this central region. Any light that's trying to come past the black hole is getting severely distorted by the existence of the black hole, which is sitting somewhere in the center of this donut. When you look at this sort of picture, you sort of get the impression that it looks like we're looking at a donut face on. So does that mean coincidentally the accretion disk happens to be face on, like a face on galaxy, for instance? Well, no. Again, because of the distortion around a black hole, it's possible that we would see an accretion disk that looks a little bit like a donut, regardless of what angle it actually forms at. This is a simulation giving us an idea of what it might look like. An accretion disk would look like a pancake if we saw it face on, but if we look at it edge on, it doesn't quite look like we would expect. It doesn't look like the rings of Saturn, for instance. Let me just run that again. It doesn't look like the rings of Saturn would look like if we saw them edge on, where we would just see a flat line. We seem to see something that looks a little bit, like an edge on Saturn's rings, but notice the distortion at the back. The sides look much like we would expect if it was an extremely thin accretion disk, but the back of the accretion disk, we see the back of the disk because the light is being distorted as it passes over the top of the black hole. Not only that, but we simultaneously see the underside of the back of the disk, because again the light is being distorted quite dramatically as it's passing past the black hole. So even when we're looking at the accretion disk at an angle, we would still probably see light all the way around the central region, which explains why we see something that looks like that. Not uniform in brightness, because it depends on the angle that the accretion disk forms, and it depends on how the accretion disk is moving. Any part of the accretion disk which is moving towards us will probably look brighter than any part of the accretion disk which is moving away from us. So at the same time they took data from the supermassive black hole in the middle of galaxy M87, they also took data from the black hole at the centre of the Milky Way, and it turns out to look very similar. It's actually a more challenging thing to image simply because it's 1,000 times smaller. Yes, it's 1,000 times closer, so it appears a similar size on the sky, but we would assume that the matter circulating in the accretion disk is moving much faster, perhaps over a period of only a few hours. So you can't simply take data and integrate all night and collect all the data you need, or all day, because the accretion disk will be moving, and if there are bright spots or dark spots, they will probably be moving over a period of perhaps even only a fraction of an hour. So they couldn't integrate the data in the same way they could with M87. So 1,000 times smaller black hole, 1,000 times closer, looks very similar, implying that perhaps the mechanics of how accretion disks form are roughly the same, even though the actual mass of the black hole is 1,000 times different. Maybe the way accretion disks form is very similar between the two. Perhaps you saw fairly recently that they've gone back to some of their earlier data and they've analysed the polarisation of the light coming from this Milky Way supermassive black hole, and they've deduced that there are magnetic fields that are polarising the light, and the streamlines, if you like, of the magnetic field are shown superimposed. If you like, it's an artist's impression. They haven't actually been able to image this. This is an indication of how they think the magnetic field lines are changing within the accretion disk, which explains changes to polarization, which they can measure. This was released only a few weeks ago. And just to remind us that the sizes are very different, if we were to plot the size of the M87 accretion disk, we'd have to remind ourselves that it's huge compared to the orbit of Pluto, for instance. And just for scale, that shows you how far Voyager 1 so far has voyaged compared to the orbit of Pluto. You can see that if the Voyager 1 had started from the centre of this accretion disk, it's only moved a distance comparable to the inner edge of the accretion disk after its many, many decades of voyaging. And if we were to draw it on the same scale, then the supermassive black hole accretion disk from the centre of our Milky Way would be barely a pixel in this image. If we blow that up, we see that the actual size of the accretion disk we're talking about in the Milky Way is smaller even than the size of Mercury's orbit, compared to substantially larger than the size of Pluto's orbit, a scale factor of something like 1,000 to 1. So we've looked at the facts, we've looked at what we mean by escape velocity, we've looked at what Einstein had to say about the existence of black holes, we've thought about the existence of stellar black holes and the supermassive black holes at the cores of galaxies, and we've looked at how LIGO can tell us about the mergers of black holes, giving us a new way of analysing the black holes that we're talking about. We can look at the accretion disk, the light from the accretion disk, but being able to measure the gravitational waves gives us a new handle on how we can study these systems. So we've looked at basically the facts. Now let's have a quick think about science fiction. We can ask the question, does Hollywood ever get it right? And to illustrate this, I've picked 3 films. The Black Hole, coincidentally, this was on TV a couple of weeks ago. I'm not sure if any of you saw it. It's a film with Maximilian Schell and Anthony Perkins and Ernest Borgnine. It's from the 1970s, if I remember rightly. In the middle there, we've got a reboot of the Lost in Space franchise. And on the right-hand side, we've got the sort of sci-fi horror movie Event Horizon. So what is the premise of each of these films that I'm trying to get a handle on here? Well, in The Black Hole, our heroes come across a ship which is parked right next to the event horizon of a black hole. Remember, at the event horizon of a black hole, time stands still. Therefore, the premise is, if you take a ship up to the event horizon, you can put on the handbrake, and as time stands still, you will just sit there quite happily. The premise of Lost in Space, forget the rest of the plot of the film, the bit I'm interested in is the fact that at the end the ship is trying to escape from a planet. It seems to be pulling away from the planet quite happily, and it seems to be escaping from the planet's gravitational pull. But then, for reasons that aren't important, the planet collapses into a black hole. And as soon as the planet collapses into a black hole, the gravity pulls the ship back again. In the third film, Event Horizon, our heroes come across a ship which is powered by an onboard black hole. So, of those 3, I'll just give you a few seconds to have a think. Of those 3, 2 of the premises are absolute rubbish, and one of them is plausible in the sense that it doesn't go against any laws of physics. I'll give you a few seconds to think about which one you think is the one that could be right and which of the 2 that are rubbish. Okay, I hope you've all made a decision and chosen either A, B or C as the one you think might be plausible. Okay, the black hole. Ship is parked right next to the event horizon. If time does get frozen or stop at the event horizon, that means time is frozen as seen by an observer some distance away from the black hole. If you were falling into a black hole, you would not notice time get any different, and you certainly wouldn't be able to park at the black hole and sit there and study the black hole knowing that time has stood still. It's purely a time relative to somebody else's clock. So no, you can't park at the event horizon. If you attempted to approach the event horizon, you will basically get sucked straight in. So number 1, rubbish. Lost in Space. Pulled back by a planet forming a black hole. Now, we don't know how to make a planet form a black hole, but remember, that doesn't matter. We're assuming it does. But if a planet suddenly becomes a black hole, the gravitational pull on an object won't change. The same mass is there at the same distance. So if the ship could escape when the planet was a planet, there is no reason to assume that the ship will not be able to escape just because the planet has become a black hole. If you think about the Earth going around the Sun, the Earth goes around the Sun in a year because it's being pulled by the gravitational pull of the Sun. If the Sun became a black hole, it would still have the same mass at the same distance, and so there would be the same gravitational pull, and the Earth would continue to go around the Sun in 1 year. Okay, there would be no light coming from the sun, so it would get distinctly chilly, but there would be no change to the gravitational pull, because that only depends on the mass and the distance. And just because you decide to compress it into a smaller space doesn't suddenly amplify the gravity. That's not how it works. So lost in space is rubbish. So that means it is possible to power a ship with an onboard black hole, if you so wished. Is a black hole powered star drive possible? Well, there's nothing in the laws of physics that say you can't do that. For instance, if you had a black hole with a mass, let's say, less than a kilogram, then you wouldn't have much energy to play with, because the maximum amount of energy you'd be able to extract from it would be E equals mc squared, and that's not much for 1 kilogram. If you had a black hole with, let's say, a mass more than the mass of Mount Everest, then the radiation from the black hole would be very weak. What is this Hawking radiation? Well, Hawking has proposed that every black hole will eventually evaporate. It will radiate, not stuff coming from inside the black hole, but just outside the event horizon. There will be a radiation coming. It's a quantum mechanical effect. We can talk about it in the Q&A if you wish, but Hawking has proposed that radiation will be very strong for small black holes, but relatively weak the larger and larger it becomes. So for a massive black hole the mass of a star, it would be extremely weak. The Hawking radiation from a supermassive black hole will be way too small to measure. But even the Hawking radiation from a mass of Mount Everest would be relatively weak, and it'd be difficult to see how you could use that radiation to power your star drive. However, if you take something in between, for instance, if you took a mass of, let's say, 1,000,000 tons, for instance, then you can calculate from Hawking's calculations how much radiation would be coming from that black hole, and it would turn out to be equivalent to something like the same amount of radiation, or sorry, the same amount of energy would be coming out of that black hole, which would be equivalent to something like 100 million nuclear power stations. That's an awful lot of energy at your disposal. 100 million nuclear power stations at your disposal. And even though that's a huge amount of energy pouring out of this small black hole, it's been calculated that this black hole ought to, in principle, last for a century or so before it finally evaporated. And then you'd have to go to the top-up filling station and get your new black hole installed to keep you going for another 100 years or so. If you had a black hole with a mass of 1,000,000 tons, it wouldn't be very large. It would only be about the size of an atom or so. And so your engine room wouldn't need to be very large. Now, I don't know quite how you would capture the radiation or how you would direct the radiation to give you the acceleration that you wanted, but that's just a question of technology. There's nothing in the physics that would stop you doing that. And I'm assuming that 100 million power stations is enough to accelerate you up to close to the speed of light and get you to the stars. What about Hollywood's fixation with shortcuts through space? If matter can warp space and time, can matter warp space enough to give you the sort of thing that we're looking at on the right-hand side there, this hourglass? Is it possible to take a shortcut through a part of space? Is it possible to distort it such that you can fall through and find yourself in another part of space? In other words, these shortcuts, sometimes called wormholes, sometimes called hyperspace, is it possible to actually do that? Well, if you believe science fiction, then of course it's possible, because we've seen Stargate and Contact and Star Wars and Star Trek. All of these movies have to have some sort of shortcut. Otherwise, the plot would be so boring if you had to spend years or decades or hundreds of years to get from one star to another. So virtually all science fiction movies use some shortcut literally as a plot device to avoid things getting too boring. But of course, if you can have a shortcut through space, really we should be talking about a shortcut through space-time. And if you can have a shortcut through space, does that mean you can have a shortcut through time? Does that automatically mean you can travel through time? And again, we've had plenty of science fiction telling us about the possibility of time travel, whether it's the time machine or the original time machine. For those of a particular age might remember the earlier version of it. But of course, we've had more recent versions of time travel, and who can forget the Doctor, of course. Again, it's tempting to think about time travel because it gives you some interesting plot lines. But of course you have problems with time travel. If you go back in time and change the past, are you changing the present? Are you changing the future? What if you kill your grandfather? Does that mean you've never existed? In which case, how can you go back in time? You have these paradoxes. And it's not obvious how we get around the paradoxes, although in principle it is possible to change space and time if you have enough mass. It's difficult to see how that can be reconciled with our ability to understand the passage of time and the paradoxes that ensue. Hawking had a conjecture. It's a conjecture because there's no way of proving this, at least not at the moment. Hawking proposed the chronology protection conjecture, which basically means a wormhole which in principle would allow time travel will actually collapse before anything has time to travel through it. So in other words, although in principle it's possible, in practice you can never actually do it. And Hawking basically said that this is one way of making the universe safe for historians. You can't change history. Now, we've got no idea if that's right or wrong. We still do not understand the principles of time travel. We don't know whether it's possible or not. All we know is that we can't find any reason why it's impossible. But we do have a problem when we're talking about black holes and other very interesting objects in the universe. We know that general relativity works really well for massive objects, like stars, regardless of whether they are large massive stars or whether they are small massive stars. Take a massive star and put it in a very small volume. General relativity has been with us for more than a century, and it's made lots of predictions, all of which have proved to be correct. It's proved itself as a theory over the last century. The other great pillar of physics is quantum mechanics, which is a theory which works really, really well for tiny objects like atoms and molecules, for instance, and subatomic particles. Again, quantum mechanics has been with us for the best part of a century. It's made lots of predictions and it works really, really, really well and has shown to be transcendent to our understanding from Newtonian mechanics. Both of these have gone beyond Newtonian mechanics. So if general relativity works really well for massive objects and quantum mechanics works really well for tiny objects, then what if an object is massive and tiny, like a black hole? Then, presumably, we need both of these theories to work together. And how do you get both of those theories to work together? Well, you can take the names and say, we need quantum gravity, which is all very well, but general relativity and quantum mechanics are not good bedfellows. It's all very well saying we've got a theory that works really well for massive objects and a theory that works really well for tiny objects, but nobody has been able to get them to work together. A universal so-called theory of everything, which takes all of the elements of general relativity and all of the elements of quantum mechanics and blended them together into a theory of everything, well, no one's got it to work. There are all sorts of mathematical reasons why when you try and apply either one to small, massive objects, you have problems. You have mathematical problems. You have infinities that you can't get rid of. Einstein never really believed that quantum mechanics was the right description of the microscopic world, so he tried working on a theory of everything. He tried to get his general relativity to work for really small microscopic systems such as black holes. He spent most of his later years wrestling with a theory of everything. This is the picture of him back in sort of 1915 or so, when he was doing his best work on special relativity and general relativity. But working for the rest of his life on the theory of everything turned this rather handsome young man into the famous picture of Einstein that we now know and love. If a genius like Einstein couldn't get his head around the problem of blending general relativity and quantum mechanics, then what will it take to get that to work? Perhaps some discoveries in the next few years or the next few decades coming out of LIGO, or perhaps coming out of the space-based version ELIZA, maybe they will point the way to a better understanding of black holes. Thank you for listening.